Let's look at what a Minimax algorithm is by playing a game of tic-tac-toe. Now, we find this game quite easy to play, but to teach a computer how to play tic-tac-toe, or better yet, to teach it to be unbeatable, is quite difficult. How we achieve this is by implementing the Minimax algorithm. It is a general purpose algorithm for game playing that determines the optimal decision to make in an adversarial game in which both you and your opponent have opposing goals. And we're going to assume that both players are trying to achieve optimal play, which is trying to ensure the best outcome for yourself, even in the worst case scenario, which is when your opponent is trying to beat you. Now, in tic-tac-toe, we have game states and we have terminal states. Game states represent any point in the game where the decisions or the actions are made and it hasn't reached the final point yet. When it does, we call that the terminal state. It is a special type of game state where no further moves can be made because the game has ended and it will either be a win, a lose, or a tie. Now, we're going to assume that the X player has the goal of maximizing the score, in which case the O player has the goal of minimizing the score. So the X player would be trying to get the +1 at every game it plays, and the O player will be trying to achieve a -1 in every game that they play. This is called an evaluation function, and it acts as a guide for the algorithm to choose the most favorable outcome for the player. Now, tic-tac-toe is an example of a deterministic two-player perfect information zero-sum game, and because it has relatively few possible moves, it is possible to map out and make an entire game tree. Um, so, first we need to create a search tree by alternating between the players. So, as you can see, the top one is the max player, and then we have the second level, which is the next player, and then it alternates back and forth at each level. This simulates decision making or thinking ahead that we find so easy to do, but it's actually really difficult for computers. Now, once the algorithm has finished its exploration, that is, once it's made its search tree, it's going to strategically backtrack so that the players will be assigned the perfect optimal outcome. For example, in this instance, what would be the optimal play for O? You might be thinking this is the optimal path. This is the optimal path. But before it reaches that, the X player can possibly win at a previous step. So this is not the optimal path. And even in this scenario, we have the exact same. So this would be our best bet, where either we draw or if the player makes a suboptimal move, we could have a chance of winning, but we eliminate the chance of losing. Now, when we backtrack, we always have to be careful that the players alternate. So, for example, in this case, at this level, we're choosing the maximum value. So the maximum of these two numbers is 4, the maximum of this is 6, maximum of this is -5, and so on. At the next level, it's going to be the minimum. So the minimum of -5 and 11 is -5, and so on. This is the pseudocode for the Minimax algorithm. As you can see, this is a recursive algorithm where the function calls itself within the function, and the algorithm is optimal, which means if correctly implemented, it will never lose a game of tic-tac-toe. It is most efficient against a random player because it's nearly guaranteed to win because of the frequent mistakes. But against a suboptimal player, the algorithm could still win, but against an optimal player, it would usually draw, um, but never lose.